Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
Good afternoon. We will continue our study of regular local rings, and today I will prove that regular local rings are UFDs. This is a good application of the last theorem. We proved that regular local rings can be characterized through the finiteness of the global dimension. I will assume that you are familiar with UFDs, except I will recall some results which you already proved and with some motivation. So, the first ring which is a UFD is ring of integers, and this is actually proved at the time of Euclid. And I guess the motivation was there. Basically, two motivations. One is, of course, the need for solving Diophantine equations, right? So, for example, solving Fermat's last theorem was also one of the problem, the solutions, etc. And it would have been very convenient if we have a prime decomposition. Then if you have two prime decomposition, then you can compare and say the exponents are equal and so on. So, that was very important, and also this actually gives you a description of a multiplicative monoid. See, if you have a ring R has a structure, it is a set with two binary operations, plus and dot, right? And with respect to plus, it is an abelian group. So, cancellation etc. happens and everything is neatly as far as the equations, also solutions and so on. With respect to the product, when it is an integral domain, then I can remove 0 and then it is still a monoid. It is a multiplicative monoid, and one would like to understand this multiplicative monoid in terms of the additive monoid. So, for example, for Z, if you look at the set of prime numbers, then this will give you the multiplicative monoid of Z, which is Z minus 0 dot. This can be described, this is a free monoid on this P as a basis. So, this is isomorphic to, you can write down, it is the sign which is plus minus 1 group under multiplication and cross n power this round bracket P. So, this gives a good description for the multiplicative. So, if you want to understand a ring better, you have to understand a multiplicative monoid better, and this understanding is done with the UFD property. So, these were done by Euclid time, and then Gauss proved this again and also noted that if I have a, generally if I have a UFD, A is a UFD, then the polynomial ring over that is also UFD. This was Gauss. Gauss actually proved it for A equal to Z, and therefore, for finitely many variables you can repeat this argument and you can get for the finitely many variables. However, for a power series ring it is not proved this way. Power series ring, this is little bit more tedious, but it is and in general it is not true also. If I have in general a UFD, then the power scissoring over a UFD may not be UFD. So, this is strange. Normally for power scissoring the results are better, but in this particular thing the result is not so good. Okay, so with this now we will assume today R is our A is our regular local ring. And we want to prove that A is a UFD. In particular, if I take this polynomial, if I take a power series ring over a regular local ring, A power series x1 to xn infinitely many variables, this is also UFD. If R is regular local, R is not a UFD, it is more than that. See, in general this is false for UFDs. So, this will follow because if R is regular local, then the power series ring over that is also regular local. Okay, so and what the ingredient you will be used is the homological dimension of any module over A has a finite homological dimension. This is what the main ingredient. Okay, so we have noticed that regular local rings by definition they are Noetherian. So, to prove UFD, we have to prove two things. Irreducible decomposition exists, that means every element, every non-zero, non-unit is a product of irreducible elements, and the second part is the uniqueness. That means if you have two irreducible decomposition, then up to a permutation, up to a unit, they are equal. So, because the ring is Noetherian, for every element has a irreducible decomposition is clear, because the chain ascending chain of ideals becomes stationary, and the divisibility can be rewritten in terms of the ideals in ascending chain. So, this irreducible decomposition exists, this is immediate from the Noetherianness. So, we have to prove the uniqueness, and uniqueness usually proved by proving irreducible elements are prime elements. So, this is usually proved by proving irreducible elements and prime elements, they are equivalent in this setup or R prime. So, we will also be concentrating proving that the irreducible elements are prime, or which is equivalent to saying again that every height 1 prime ideals are principal. So, because if you have a height, if you have a prime ideal, then it will have an element in that, and that non-unit you can express it at a irreducible decomposition, and therefore, because the ideal is prime, it will contain one of the element, and because height is 1, it has to be equal, and that will be therefore a generator will be a prime element, and that is how the proof is go. So, therefore, we have to concentrate on proving every height 1 prime ideal in a regular local ring is a principal. So, that is the main step. Okay, now, before I go on, I just want to also recall you what is the definition of a prime element in general in a ring. So, an element P in the ring A, in general not even a domain, is called prime. If first of all P has to be non-zero divisor. Normally one assumes, when you talk about this concept, one assumes you are in integral domain, but you may not In general, you may not be in integral domain. In that case, an element is called prime if P is a non-zero divisor and ideal generated by P is a prime ideal. Or equivalently, if P divides A times B, A, B are elements in A, then P divides A or P divides B. So, the theorem actually we will prove is so this is the theorem we will prove. AM regular local, then A is a UFD. As you will see, this proof is not so difficult now because the major work has gone into the earlier theorem, that homological characterization of the regular local ring. Okay, so first let us just note the lemma which I will use it, and this lemma is valid for not necessarily local ring, it is valid for any Noetherian ring. So, I will state in that generality. So, lemma A is Noetherian and A is an ideal, A is ideal, non-zero ideal. Suppose A is projective, projective as A module, and that A has a finite free resolution by free modules of finite rank. This means, so that is, let us spell out what does it mean. This means you have an ideal A here, we can have a resolution like this. Finite length of the resolution, and all these modules are free, A modules of finite rank, but that means they are finitely generated free modules. They have the basis of finite cardinalities, that is what given. Then the conclusion is, then the ideal A is free of rank 1. In particular, A is principal. Proof is very simple. Let us finish off the proof. I want to show it is free of rank 1. What is given? So, let A is a non-zero ideal, and also if A is equal to A, there is nothing to prove. So, we might as well assume A is a proper ideal. So, then I can always find a prime ideal, choose a prime ideal, choose P prime with A is contained in P. It is a proper ideal, it is contained in some maximal ideal, in particular prime ideal. Once it is contained there, and then when I localize Now from the ring A, I go to the localization A localized at P. We had an ideal A here, proper ideal. We get a ideal A localized at P. This will also be proper ideal because A is contained in P. And now what we had given was A is a projective module. So locally it is free. Projective modules or local rings are free. So in particular this A localized at AP is a free. So A this module, this ideal is a free A localized at P module. But this is an ideal in a local ring which is free, therefore it has to have rank 1, because any two elements in ideal they will be linearly dependent. Therefore the rank can if the rank is more than 1, it will have basis consisting of more than one element, but that is not possible because any subset which has more than one cardinality has to be linearly dependent. So therefore rank of this module has to be 1. Okay, and what is that we want to prove? We wanted to prove that A is free of rank 1, but locally we proved A is free of rank 1. Okay, and we have a finite free resolution, so that will tell you there exist finitely generated free A modules F and G such that A direct sum F is isomorphic to G. This you prove it by induction on the length of the free resolution you have given, because the module is projective, therefore you can add something so that it becomes free, but you can the other component may not be free, but you can add more and then make it free. So therefore you keep doing this. So by adding a free module you get a free module. But when you localize this, then localization comes with the direct sum etc. So A this direct sum F localized at P is isomorphic to G localized at P. Therefore rank of G which will be rank of the localization. So we write down rank of G which is rank of G localized at P, which is from here, this is rank 1, this is whatever rank. So this is 1 plus rank of FF, which is 1 plus rank of F. So therefore A has to be of rank 1. So that implies a rank of A is 1, and it is, once it is rank 1 it is free, and once it is free it is principal, and the ideal A is free. Okay, so this is I will use it. I may not use in this generality, I may even use it in a one more special case of this lemma, which will be even more easier than proving what we have proved it now. Now start with the regular local ring. We are assuming it is regular, and as we saw, enough to prove that if you have a prime ideal P, height of P is 1, then P is principal. And this I am going to do it by induction on the ring, dimension of the ring. We will prove this. By induction on D equal to dimension A. We know dimension is finite because A is a local ring. So, let us, for D equal to 1, we have a regular local ring of dimension D. Therefore, this D is also same as minimal number of generators for the maximal ideal, which is the dimension of the vector space M by M square, which is also called the embedding dimension of A. Okay, suppose D is 0, that means what? That means this vector space is 0 dimensional vector space. That means it is a 0 vector space. So, then M by M square is 0, which means M equal to M square, but that means M is 0 by Nakamelum. But once the maximal ideal is 0, you are in a local ring, therefore, actually A is a field, and there is no prime ideal, there is nothing to prove. Okay, so assume now dimension is at least 1 and let P be a prime ideal height P equal to 1. Height P is 1, so it is in a local ring, so P definitely contains 0. 0 is a prime ideal because regular local rings are domains. So, this is not, and because this is a local ring, this P is contained in the maximal ideal M. So, if, and also we know that D is at least 1, so M cannot be M square, because this D is the dimension of this M by M square, so it cannot be 0 vector space. So, definitely I can choose, so choose T in M minus M square, and we have seen that when I go mod T now, A by AT, this ring is again regular, because we have gone modulo part of a regular system of parameters. So, this T can always extend it to a generating set for M, because it is a non-zero element in vector space, can always be extended to a basis. So, this T x1 xd, this is a minimal set of generators for M. Anyway, it is a regular local ring again. All right. So, therefore, in particular this AT is a prime ideal, because this is a regular local ring, it is an integral domain, therefore, AT will generate a prime ideal. This is a prime ideal in A. And therefore, it cannot be contained in, if it is contained in P, then P has to be equal to AT, because height P is 1. So, if AT is contained in P, then P has to be equal to AT, is principal, and we had finished our proof to prove that P is principal. So, we may assume T is not in P. Okay, we have assumed T is not in P. Therefore, if I take this multiplicative set S generated by T, that is 1 T, T square, etc., this multiplicative set will not intersect with P. So, S intersection P is empty. Therefore, when I go from A to S inverse A, this P here will survive here. What do I call that? Okay, I just called it S inverse P. This will not be equal to S inverse A. Let us call this ring as B. So, this P will be this is image of P. This is a prime ideal in B. Okay, so instead of writing this S in S in S, I will write B, and this one is therefore PB. So, we are in the situation like this now. A was our original regular local ring. We have localized that at this multiplicative set. And remember that this may not be local now. But what we know is, if you have a prime ideal here, that remains prime here. Okay. And now, if I want to prove P is okay, our aim is to prove P is principal. Remember that. Okay. So, I will prove this in 3 steps. So, how will I prove it? I will prove it like that. Step 1, I will first prove that this ideal PB is a projective B module. All right. So, to prove somebody is a projective B module, it is enough to prove that it is locally free. It is a finitely generated, so it is enough to prove that it is locally free. So, enough to prove that PB is locally free. That is, I have to prove that if I localize this at any prime ideal of B, it is free. So, that is, I have to prove that P, B and localize at capital P. This is free BP module for every prime ideal P of B. But we know the prime ideal structure of this B, they are coming from A, those who do not intersect with S. So, therefore, this capital P look like capital P prime B, where capital P prime, this is a prime ideal of A and it do not intersect with S, with P prime intersection S is empty. Clear, no? If all prime ideals of this B, they are coming from the prime ideals of A who do not intersect with S. So, I have taken capital P, arbitrary prime ideal of B, which will be P prime, where P prime is actually prime ideal in A, who which do not intersect with S. But such a P prime cannot contain T. Note that T cannot be contained in P prime, because P prime do not intersect with S and S is generated by T. So, P prime cannot be in T cannot be in P prime. So P prime cannot be M, because M contains T. So, therefore, P prime is a prime ideal of A which is not the maximal ideal. That means the dimension of A localized at P prime, this will be strictly less than dimension of A, which is D. This is height of P prime, and height of P prime cannot be the full dimension. Height of D is height of M. And remember, we have proved that if A is regular local, then all localizations are regular local. So therefore, A localized at P prime is again a regular local. This is by the corollary to the earlier theorem that global dimension is finite. This we cannot directly prove from the definition of. Okay. So, and what is it? And this P small p A localized at P prime, this capital, this is what we wanted to prove, it is principal, right. Our aim was to prove that P is principal, but when I prove that P is principal, I am proving it in a localization, it is principal. So therefore, this is principal by induction. No, I don't even want to note that. So look at this prime ideal. This is same as P B localized at capital P. So here B was S inverse of A, and this P prime don't intersect with S, and so whether you localize at B localized at P and A localized at P prime, they are same. See, because this P prime is so see, remember this capital P was P prime B. So when I localize further localization, that is same as this. So this prime ideal is same as this. So therefore this is principal by induction. So P A localized at P prime is principal by induction on D, because this dimensional drop. Since dimension of A localized at P prime is strictly smaller than D. Once it is principal, it is free, and hence P A localized at capital P prime is free, but then this is free, and that is what we wanted to prove. We wanted to prove it is locally free. So what we proved is, therefore we have concluded that if I take this P and extend it to B, this is a projective model. This is what we wanted to prove in step 1.